In previous videos, we talked about the first pattern for recognizing resonance, and that's when you have an allylic lone pair. And in exercise 226, we see a second pattern. That's when you have an allylic positive charge. That's a positive charge that's one atom away from an atom in a double bond. So you only go one atom over, and you're at an atom in a double bond. So when you have an allylic positive charge, what ends up happening is that those electrons in the pi bond go to form a new pi bond toward the positive charge. That's the curved arrow pattern that accompanies that. And so here's some practice with those. Now in this first structure, every time you see a new structure, although we're ordering them now so that it's clearly an allylic positive charge, you might see them mixed up in a test, and so it could be any pattern in any order. So what you'd want to do is go one by one, methodically, from the left to the right of these 5 patterns, and see whether you have one of them. So first check for allylic lone pairs. We don't have that in this structure. We don't have any lone pairs there. Carbon only has a lone pair when it has a negative charge. But we do have an allylic positive charge, right? This positive charge is one atom away from an atom in a double bond. And so what happens when you have an allylic positive charge is that the pi electrons go toward the positive charge and to form a new pi bond there. So you have a resonance structure, you have a resonance pattern, so instantly you want to warn the world by drawing those brackets, the brackets that tell you none of these structures inside here is the true structure is the average of them. And then draw that special resonance arrow with the one line and 2 heads that tells you to take the average of these. So the first step is just to copy the molecule exactly as it is. You can erase you don't have to include the curved arrow. And one thing that is a little useful is to draw in the hydrogens. That'll make it easier for you to calculate the formal charges after you move the electrons around. So this carbon here has no formal charge, and it needs 4 total bonds. Only 1, 2 are drawn, so it has 1, 2 hydrogens on it. This carbon here has no formal charge, so it needs 4 bonds total. Only 1, 2, 3 are drawn, so it needs 1 more, and that would be to an invisible hydrogen. This carbon here needs 3 total bonds because it has a positive charge. A carbon with a positive charge has only 3 bonds because it's 4 minus, it doesn't have any lone pairs, and then you need 3 bonds in order to get the positive 1, so 3 lines. So if you have a carbon with a positive charge, just keep in mind it needs 3 bonds. 1, 2 are already drawn, so you just put in a 3rd one to an invisible hydrogen. And this last carbon we don't have to worry about because the curved arrow is not going toward that. It's not affecting that. The formal charges change because electrons move and bring their charges with them. All right, so now that we've looked at those hydrogens, we can look at the curved arrows. Now, anywhere where you have the tail of a curved arrow, those electrons are moving. And so they're moving away from there, so you want to erase those. And anywhere where the head of a curved arrow is pointing, you want to add electrons, because electrons are going toward there. If the head of a curved arrow points at a bond, then you draw in the electrons as a new bond. All right, then we just go through and calculate the formal charges. Notice with this carbon here, that carbon has 4 minus 0 dots, and it has 4 lines around it. 1, 2, 3, 4. So that has a 0 formal charge. It doesn't still have that positive charge. If you go through the same process with this carbon, you'll see it's the same thing. 0 dots, 4 lines, so it has a 0 charge. And if you go through the process for this carbon on the right, 4 minus 0 dots plus 1, 2, 3 lines, that now has a positive 1 charge. So that has this positive charge here. And so you just erase the hydrogens because it's a bond line structure, so those should be implied rather than explicit. And that would be your resonance structure for this molecule. The true structure doesn't look like either of these. It looks like the average of the two. So the true structure, the fancy term for it is the resonance hybrid, would look something like this. A slight positive charge here and a slight positive charge there. So these bonds are somewhere in between double and single. And the charges are somewhere in between 0 and positive 1. Right. So let's go through that same process for B. So here, notice, so you go through the 5 patterns. We don't have an allylic lone pair here because we don't have a lone pair at all. Carbon only has a lone pair when it has a negative charge. We do, however, have an allylic positive charge. This positive charge is 1 atom away from an atom in a double bond. You only have to go 1 atom over to be there. So it's allylic. And so we have resonance. So you'd draw in, you'd say, oh man, draw those big brackets that let people know that this is not the true structure. The true structure is the average of this and another structure. And then draw in that special resonance arrow that tells people to take the average of these. And anytime you have an allylic lone pair, the pi electrons go to form a new bond toward the positive charge. That's just the curved arrow pattern associated with that. So you can take that same structure, copy it, and just redraw it over here, just without the curved arrow. And in order to find the formal charge, see how the formal charges change more easily, we just want to draw in some hydrogens. Now notice the only carbons whose charge could possibly be changing are these, because those are the only carbons that electrons are moving around. Those are the only carbons associated with that curved arrow. So let's draw the hydrogens on those. This carbon has no formal charge, which means it needs 4 bonds total. 3 are already drawn, and so it just has 1 more to an invisible hydrogen. Same with this one. It has no formal charge, so it needs 4 bonds total. 1, 2, 3 are already drawn, and so it would just have 1 invisible hydrogen. This carbon here has a positive formal charge. Remember, when carbon has a positive formal charge, it only has 3 bonds. This way, when you do that formal charge calculation, 4 minus 0 dots plus 3 bonds, or 3 lines, you get the positive 1. So that only has 3 bonds. Let's see how many are drawn in. 1, 2, that means there is a third one, an invisible third one to an implied hydrogen. So those are the hydrogens that we have to worry about. All right, now let's think about the curved arrows. Anywhere where there's a tail of a curved arrow, those electrons are moving away from there, so you erase those. Anywhere where there's a head of a curved arrow pointing, electrons are arriving there, so you draw those in. If the head of a curved arrow is pointing at a bond, then you draw in a bond. All right. Now, let's go back and just check the formal charges. For this carbon on the left, it's 4 minus 0 dots around that carbon, 3 lines around that carbon, and so that carbon now has a positive 1. The middle carbon is the same. 4 minus, there are no dots around that carbon, there are 4 lines around it, and so that has ultimately a 0 charge. And for the carbon on the right, it's carbon, so 4 minus 0 dots around it. There are 4 lines around that now. 2 in the double bond, and then 2 in the other single bonds. And so that has a 0 charge, not this positive charge. So once you put the formal charges in, you can erase those hydrogens. Those should be implied in these bond line structures. And so that is your molecule. The true structure is not either of these. The molecule never looks like this. It also never looks like this. It always only looks like the average of those two. If I were to try to draw it out, it would look something like this. That's the only way the molecule ever looks. And just a way of sort of communicating this a little more precisely is with these resonance structures. All right, let's continue this pattern with C and D. So for C, you'll notice that we don't have any, we'll look back at that first pattern, we don't have any lone pairs, so we don't have any allylic lone pairs here. Carbon only has a lone pair when it has a negative charge. However, we have a positive charge, and the positive charge is allylic, because if you go just one atom over, you end up at an atom in a double bond. So that positive charge is allylic. So we're going to have resonance, and so we'll draw those big fat brackets to warn people, let them know. And actually here, let me draw those right here. And so we'll draw our structure in, and those brackets are warning people, watch out, none of the structures here are going to be the real structure. The real structure is the average of them all. And to take the average, you draw that special resonance arrow. Okay, eventually we will have these brackets there. Okay, so whenever you have, and actually just while we're doing this, let's fill the hydrogens in now, so they'll follow us through. I'm just going to do that quickly. You'll see that this one is very similar. The process of figuring out the hydrogens is very similar to B. So this carbon here, all the carbons except for this one, all the other carbons in the molecule have zero formal charge. So they all need 4 bonds, except for the one with the positive charge. So this one only has 3 drawn, so it needs 1 more. The carbon at the top left only has 3 drawn, so it needs 1 more. At the bottom right only has 3 bonds drawn, so it needs 1 more. At the very bottom, only 3 bonds are drawn, so it needs 1 more. This carbon at the bottom right only has 2 bonds to it drawn, so it needs 2 more hydrogens. All right, finally, this carbon with the positive charge, any carbon with a positive charge needs only 3 bonds, as we explained in A and B above. And so that carbon has 2 bonds drawn, it needs 3, so there's just 1 hydrogen there. And we went through this and drew in those hydrogens, not because we want them to stay there, but because that will help us calculate the formal charge more easily in the future. Okay, so let's draw our curved arrow pattern in. Whenever you have an allylic positive charge, the pi bond electrons go toward the positive charge. So let's move these over. So take that structure, and now we can think about that, and just copy the structure, and we can think about that curved arrow. So anywhere where you have the tail of a curved arrow, that's a place electrons are moving away from, so erase those. Right? These electrons here, you would erase those. Anywhere where you have the head of a curved arrow pointing, that's where the electrons are arriving, and so you'll draw the electrons there. Now if the head of a curved arrow is pointing at a bond, then you draw the electrons as a bond. Right, then you just want to check to see how the formal charges have changed. Notice that this carbon now has 4 lines around it, and so it has a 0 charge. Notice how this carbon now has 4 lines around it, so it has a 0 charge. This carbon, the only other one that was affected, has only 3 lines around it, so 4 minus 0 dots, 3 lines, that's positive 1. So that carbon has a positive charge. All right. Now we've drawn one resonance structure, but there's no rule that says a molecule can only have two resonance structures. So long as you have a resonance pattern, and you can draw, so long as you have a new resonance pattern, you can draw another resonance structure. So for example, here we have a positive charge, and this positive charge is allylic. Now technically it's allylic to two pi bonds. It's allylic to the pi bond at the top. If you go one atom in that direction, then you arrive at an atom in a double bond. So it's allylic to that. But if those pi electrons just went back towards here, that would bring you back to this structure. So that would just take us back to where we've already been. You can, however, draw a new resonance structure because the positive charge is also allylic to the other pi bond. If you go one atom down from the positive charge, you end up at an atom in a double bond. So it's also allylic to that. So we should draw the resonance structure that results from the curved arrow of this pi bond going to that positive charge. Now if you run out of space, you can definitely start drawing these vertically, just however you need to fit them in. Normally the best practice would be to draw them left to right, but again, if you run out of space, not a big deal. So you would just want to make sure the brackets include everything. Okay, so we'll draw our structure. The first step is to copy the one that we're working from. And anywhere where you have the tail of a curved arrow, those electrons are going to be moving away from there. So you erase those. And anywhere where you have the head of a curved arrow, electrons are going to be arriving there. So you draw those in. If the head of the curved arrow is pointing at a bond, then you draw the electrons that are arriving as a bond. And let me move this positive charge just so it doesn't overlap and look confusing with that bond. I'll just move it right there. Okay, so now that we've moved the electrons, we just want to look at the formal charges, see how those have changed. Notice this carbon here now has 4 bonds around it, so it has a 0 formal charge. This carbon has 4 bonds around it, 4 lines, so it has a 0 formal charge. But this carbon at the very bottom has only 3 lines around it, so 4 minus 0 dots, 3 lines. That gives that a positive formal charge. So that is our new resonance structure. And that we have a positive charge there now. It is technically allylic, but if it were to go back, if this were to go here, we would just end up with the structure we had above, which we've already drawn. So these are all of the different ways you could draw this molecule. The true structure is the average of these 3. All right, let's erase the hydrogens. We were just using those so that it was easier for us to see the new formal charges when the electrons moved around. And actually, just so it's a little easier to see, I'm going to put all of these just in a straight line. All right. So this structure had 3 resonance structures. This molecule had 3 resonance structures. What does that mean? Remember, the more resonance structures you have, the more stable the molecule is, because the more charge is being spread out. And also the more rigid the molecule is, because the more bonds there are that can't rotate because they have pi bonds in them, associated with them. So this molecule, which has 3 resonance structures, is more stable and more rigid than, say, this molecule, which only had 2 resonance structures, or another molecule that had none. Also, let's average these. Let's try what the real molecule looks like, just for the sake of giving some more meaning to this. So the real molecule would have intermediate bonds all the way around here, and it would have a slight positive charge at this carbon, and at this carbon. Notice how different that is than the first structure that we saw. If there were a negatively charged molecule that we were going to react with this, where would it attack? Well, if we only saw this one structure, this negative charge would be attracted to this just one positive charge here. We'd think it would only attack one place. But when we look at the true structure that we get from averaging the resonance structures, we see that there are actually going to be 3 places on the molecule that it would want to attack. The positive charge there, or at the bottom. And so you could imagine this attacking this carbon here. But the only way you'd know why is by drawing a resonance structure that has the positive charge there. So drawing these resonance structures, 1, gives us a sense of the stability and rigidity of the molecule, and 2, lets us visualize where the molecule may react in a way that we might not otherwise have seen. All right, last but not least, this structure, and this is going to be very similar to the one we just did. Just for the sake of time, I'm going to assume that by this point you are able to calculate the formal charges on these carbons. And if you have trouble with that, just make sure you go back and follow each of the previous examples very carefully, step by step. So I'm not going to draw the hydrogens for this, just for the sake of time. But I do encourage you to draw them, especially as you're first going through this. So notice, this positive charge is allylic, because when you go just one atom over, you're at an atom in a double bond. So that's allylic. Anytime you have an allylic positive charge, the pi bond that you're allylic to, those pi electrons go toward that positive charge. So you draw the resonance arrow, copy the molecule, and so anywhere where you have the tail of an arrow, those electrons are going to be moving away from there, so you erase those. And anywhere where you have the head of an arrow, the electrons are going to be arriving there, so you draw those in. If you go through drawing all the hydrogens and using the formal charges, you'll see that this positive charge isn't there anymore, and that it reappears here. And so now you have that positive charge is allylic to a new double bond, this double bond here. It's also allylic to this, but if this moves back, you just end up with your original structure. So we'll draw this, and let me actually do this. I'm going to draw the arrow left and right like this, but I'm going to include my next structure at the bottom here. So I'll take this, copy it, and now anywhere where I have the tail of a curved arrow, that's a place where electrons are moving away from, so I erase that. Anywhere where I have the head of a curved arrow, that's a place where electrons are arriving, so I draw those in. If the head of a curved arrow is pointing at a bond, like it is here, then I draw in a bond. Now if you draw out all the hydrogens and you calculate things like we've been doing before, you'll find that this charge should be a 0 charge, and you should have a positive charge here. And this is now allylic to a new double bond. That positive charge is allylic to this new double bond, and so the pi electrons in that double bond go toward the positive charge. So you draw your resonance arrow, you copy the structure, anywhere where there's the tail of a curved arrow, that's where electrons are moving away from, so you erase those. Anywhere where there's a head of a curved arrow, that's where electrons are going, and so you draw those electrons in. If the head of a curved arrow is pointing at a bond, like it is here, then you draw the electrons as a bond. If you go through and draw all the hydrogens, you'll see that this positive formal charge would go away, and you would get a new positive formal charge here. Okay, so just to keep track, these are the places where we've had a positive charge so far. We've had it at the top, we've had it at this left area, at the right area, we've had it down here, and we've had it here. Now, this is now allylic to a new pi bond, this bond right here. So these pi electrons can go toward the positive charge and give us a new resonance structure. To draw that new resonance structure, you would see anywhere where you have the tail of a curved arrow, that's where electrons are moving away from, so erase those. Anywhere where you have the head of a curved arrow, that's where electrons are arriving, so you want to draw them in. If the head of a curved arrow points at a bond, then you draw those electrons arriving as a bond. And if you were to calculate all the formal charges, you would see that this one would disappear, and you'd have a positive charge up and to the right. So now we have this slight positive charge here. Okay, well now this is allylic to this positive charge is allylic to a new pi bond, this one here. So that can go towards the positive charge, we get a new resonance structure. To draw it, we copy the one we have, and anywhere we have the tail of a curved arrow, that's a place where electrons are moving away from, so you erase those. Anywhere we have the head of a curved arrow, that's where electrons are arriving, so you draw them in. If the head of a curved arrow is pointing at a bond, then you draw the arriving electrons in as a bond. And what you'll find if you calculate the formal charges correctly for that is that this here should be 0, and you should get a positive charge here. So now we see that the positive charge can go right here. Last but not least, that positive charge is allylic to one more pi bond, this pi bond here. So that pi bond goes toward the positive charge, and we get our new resonance structure. Let me just make a little room for that. All right, our new resonance structure. So we have a new arrow. All right. And so you copy the structure you have. Anywhere we have the tail of the curved arrow, that's a place where electrons are moving away from, so you erase those. And anywhere where the head of a curved arrow is pointing, that's a place where electrons are arriving. And so you draw those in. If the head of a curved arrow is pointing at a bond, then you draw those arriving electrons as a bond. And if you draw all the hydrogens in and you calculate all the formal charges, you would see that at the top left here, that charge becomes 0, and you end up getting a positive charge at the bottom. And so we also have a slight positive charge there. Okay, so this had a whole bunch of resonance structures. Now notice, if you go through the same process and you move this over again, you would get the positive charge at the far right. That's the structure we started with. So the structure would be repeating. So this is the last resonance structure, because if you continue doing what you've been doing, the structures start repeating. So this structure had 1, 2, 3, 4, 5, 6, 7 different resonance structures. What does that mean? It means that this molecule is first really stable. Second, it's really rigid. So very stable, very rigid. That means it'll be a good chemical messenger. Because it's stable, it'll survive It'll be able to pass through places without degrading or turning into something else. And because it's rigid, it will reliably fit into a receptor site. And it also lets us see places where there's positive charge where we wouldn't have guessed in this original molecule. The true molecule would look something a little bit like this. So all of these bonds are something in between single and double bonds. And every single place, every single carbon has a slight positive charge. So that's a very different structure than just this molecule here. So every single one of those carbons will attract a negatively charged thing. Okay, so that is our second resonance pattern, doing some practice with our second resonance pattern, the allylic positive charge.